In this problem, we're going to find I0 of t for t greater than 0 using the step-by-step method. The problem-solving strategy that we're going to utilize is entitled Using the Step-by-Step Approach. Step 1 of this approach says that we know the form of the solution is I0 of t is equal to K1 plus K2 e to the minus t over tau. We've got a capacitor out on the right hand side. We've got DC sources. Different in this one compared to some of the others is we have a dependent source, so we're going to need to deal with this, and really where it's going to impact us is when we go to calculate the Thevenin resistance seen by the capacitor. So utilizing our problem solving strategy, let's draw the circuit at t equals 0 minus. We're going to assume steady state, so the capacitor will be replaced by an open circuit. And what we're going to do is we're going to solve for the capacitor voltage, VC 0 minus, because we know that's going to be the same at 0 plus. So we could do mesh or nodal, either one. We'll do is let's go in and let's pick nodal, and what I'm going to do is I'm going to pick that as a reference, and I'm only going to have one node voltage. I'm going to call this one V1 prime. And the reason you say, well, you have another node here, yeah, but since that's 0, then we know by KCL that this current's going to flow in there, so there's really only one node voltage here. Okay, so let's apply nodal analysis. So now we have V1 prime minus 12 over 6K. That's the current going that direction. Then we have V1 prime over 4K, the current flowing down, and that's equal to 2IA prime. And if we look in our circuit, IA prime is 12 minus V1 prime over 6K. So now let's substitute that in. So we have V1 prime minus 12 over 6K plus V1 prime over 4K is 2 times 12 minus V1 prime over 6K. And if we rearrange terms, we can get V1 prime times 1 over 2K plus 1 over 4K is equal to 6 milliamps. And we can solve for V1 prime is equal to 8 volts. Now we can solve for IA prime. We have 12 minus 8 over 6K. So this is 2/3 of a milliamp. Now, to calculate that capacitor voltage, we can do KVL around this loop. So, for instance, if we look for a second, this source has a value of 4/3 of a milliamp then. So there's 4/3 of a milliamp here in the circuit. And then that tells us that there's 4 volts across that 3K resistor. So then VC0 minus is 4 plus V1 prime, 4 plus 8, and that gives us that initial capacitor voltage is 12 volts. Now that completes our analysis at t equals 0 minus. Now our next step is to go to circuit at t equals 0 plus. Notice that we've replaced our capacitor with a voltage source of 12 volts. And now we need to find the current flowing through our 4K resistor. And again, I'm going to use nodal analysis. If I look, there are several nodes, but if you notice, a couple of them, for instance, this one and this one, are known. So I have a couple of node voltages here unknown, V1 double prime, and I'll call this one V2 double prime. So now we're going to need to write two equations. So starting on the left, we'll have V1 double prime minus 12 over 12K plus V1 double prime over 4K plus V1 double prime minus V2 double prime over 3K equal to 0. That's a KCL equation at this node. We can reduce this to 2/3 V1 double prime minus 1/3 V2 double prime is equal to 1. Now let's go in and apply KCL here. And if we do that, we'll have V2 double prime minus V1 double prime over 3K plus V2 double prime minus 12 over 3K, and that's equal to 2IA double prime. And if we look at our circuit, we can see IA double prime is 12 minus V1 double prime over 12K. Now if we take this and substitute in here, what we get is minus 1/6 V1 double prime plus 2/3 V2 double prime is equal to 6. So now we have our two equations, and if we solve for V1 double prime, it turns out to be 48 over 7 volts. So I0 at t equals 0 plus then is 48 over 7 over 4K, and that's 12/7 of a milliamp. Okay, so that concludes our analysis at t equals 0 plus. Now we need to go to the circuit at t equal infinity. Now we're going to assume the circuit's in steady state again. The capacitor is replaced by an open circuit. And again, we need to find I0 of infinity. I'm going to select this as a reference node. Again, we note this is 0. We have one node voltage here, V1 triple prime, and what we'll do is we'll apply KCL here to come up with a nodal equation. So we'll have V1 triple prime minus 12 over 12K plus V1 triple prime over 4K is equal to 2IA triple prime. And from the circuit, IA triple prime is 12 minus V1 triple prime over 12K. Now we'll take this, substitute into there, and when you do this, you can get V1 triple prime is 6 volts. So I0 of infinity is 6 over 4K, which is 1.5 milliamps. Now, while we're here, let's calculate VC of infinity. Okay, so to do that, let's calculate IA triple prime. So IA triple prime then is 12 minus 6 over 12K, which is 0.5 milliamps. So this source has a value of 1 milliamp. So that tells us that there's 1 milliamp here. And then that tells us that there's 3 volts across that 3K resistor. So now we can get VC of infinity really by going around this loop. So VC of infinity, we have 0 there, we have 3 volts here and then 6 volts, so VC of infinity is 9. Now we're going to use that in just a second. I thought I'd go ahead and calculate it while we were at this circuit. Now we need to calculate the time constant. Now, since we have a dependent source, remember we're going to have to calculate the open circuit voltage and the short circuit current. So if we look in step 5 of calculating the time constant, we need R Thevenin. The open circuit, we want the time constant of Thevenin resistance as seen by the capacitor. So when we calculated VC of infinity, that was also the open circuit voltage. So we've already calculated the open circuit voltage. Now we need to calculate the short circuit current. So here's our circuit for calculating the short circuit current. And again, we've been using nodal analysis. Again, let's continue. Now we'll have V1 with 4 primes, and we'll have V2 with 4 primes. Okay, and so now we're going to have 2 equations. We're going to do KCL at those 2. So at the left, we'll have V1 minus 12 over 12K plus V1 over 4K plus V1 minus V2 over 3K equal to 0. And we can reduce this equation to 2/3 times V1 minus 1/3 times V2 equal to 1. So there's our equation at the left node. At the right node, we'll get V2 minus V1 over 3K. Then we'll have V2 over 3K is equal to 2IA prime, or quadruple prime. And again, we note from the circuit that IA quadruple prime is 12 minus V1 quadruple prime over 12K. So now we would take this, substitute in here, and our equation becomes minus 1/6 V1 plus 2/3 V2 equal to 2. So here's our second equation. Now if we solve, we get V2 quadruple prime is 27 over 7 volts. So then I short circuit is 27 over 7 divided by 3K. So I short circuit then becomes 9/7 of a milliamp. So now we can calculate the Thevenin resistance. R Thevenin is V open circuit over I short circuit. So we have 9 volts divided by 9/7 of a milliamp, and that gives us 7 kiloohms for the Thevenin resistance. So our time constant then is 7K times 100 microfarads, 0.7 seconds. And then the final step in our solution is we know the form of the solution. That's just a matter of plugging in. So now we have 1.5 plus 12 over 7 minus 1.5, either the minus t over 0.7 milliamps. So then I0 of t is 1.5 plus 0.2143 e to the minus t over 0.7 milliamps.